Today we're going to talk about gravitational fields, which we use to explain how the gravitational force acts. Gravity is a field force. That means, unlike normal force and friction, tension, and other forces we've seen before, gravity doesn't require contact for the force to be present. So how's gravity able to exert a force? It acts through the interaction of gravitational fields. Every mass has a gravitational field in the space around it. We can't see these fields, but we can use a model to visualize them. Here's the Earth zoomed way out. If we held a rock high above its North Pole and dropped it, which way would it fall? Well, it'd fall down. What about if we held it above its South Pole? The rock would still fall down towards Earth. No matter where we hold the rock, it'll fall towards Earth. This is an example of a varying gravitational field. If we zoom in close enough so that the Earth appears flat, we hold that same rock, which way is it going to fall? It's going to fall down, obviously. Wherever we hold it, that rock falls down. This is an example of a uniform field. These arrows we drew are called field lines. They allow us to visualize the gravitational field. They show the direction of the gravitational field, and the density of the arrows give us an idea about how strong the gravitational field is. The field lines provide a qualitative representation of the field. When the fields of two or more objects interact, it results in a gravitational force. The field strength determines how strong the force will be when the fields interact. The field strength is equal to g, the gravitational constant, times the mass divided by the distance or the radius squared. Field strength does not depend on the mass of the quote-unquote rock. It exists even though no other masses are present. This is also another example of an inverse square law. The field strength at a given point is equivalent to the acceleration due to gravity at that point. So we can say the strength of the Earth's gravitational field at its surface is 9.8 newtons per kilogram. 1 newton per kilogram is equivalent to a meter per square second. Since field strength and acceleration due to gravity are equivalent, we can use Newton's second law to find field strength. We can find the strength of a gravitational field by dividing an object's weight in that field by its mass. Let's work through a couple example problems. Number 1, find g for the surface of the moon. Its radius is 1.7 times 10 to the 6th meters, and its mass is 7.4 times 10 to the 22nd kilograms. We can find the gravitational field by multiplying the gravitational constant by the mass of the moon divided by its radius squared. So you have 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 7.4 times 10 to the 22nd kilograms divided by 1.7 times 10 to the 6th meters. And that quantity is squared. So like we did before, we'll multiply the top of the fraction first and then we'll do the bottom. So we have 6.67 times 10 to the negative 11th times 7.4 times 10 to the 22nd, which gives about 4.9 times 10 to the 12th. So at the top of the fraction, we've got 4.9 times 10 to the 12th. On the bottom, we have 1.7 times 10 to the 6th. And we're going to square that, which gives us 2.9 times 10 to the 12th. So we have 4.9 times 10 to the 12th divided by 2.9 times 10 to the 12th. Our 10 to the 12s cancel out, so we're left with 4.9 divided by 2.9, which is 1.7 newtons per kilogram. For number 2, compute g for the surface of the planet whose radius is twice that of the Earth and whose mass is the same as that of the Earth. To find the gravitational field, we're going to use the relationship between the gravitational field and the distance, and it's an inverse square law. So we're doubling the radius while keeping the mass the same. So we're going to square that 2. 2 squared is 4. Take the inverse of 4, gives us 1/4. So the gravitational field would be 1/4 of g. 1/4 it is what it is on Earth. So 1/4 times 9.8 gives us 2.5 newtons per kilogram. For number 3, an astronaut with a mass of 80 kilograms experiences a gravitational force of 298 newtons on Mars. What is the gravitational field on the surface of Mars? So to find the gravitational field, we're going to do the weight of the astronaut divided by his mass. So we have 298 divided by 80, which is 3.7 newtons per kilogram.